Hey, today I wanted to talk about receptive fields and the role of glutamate and GABA, as well as different channels in bipolar cells affect whether we send an action potential or not. It's interesting how some things inhibit which allow signals to go. So we'll kind of jump into that a bit today. But to start out, let's go on with just some basic functions of certain channels, as well as what cells do certain things, okay? So what are receptive fields to start? They help us see sharp contrast and edges. So if on an edge you have a dark side and a light side, certain action potentials will fire through bipolar cells, so that you can see, oh, this is an edge, there's a dark side to it and a light side. And light is going to hit photoreceptors in certain ways that will allow us to distinguish those differences. Light typically will deactivate things, or in photoreceptor cells will hyperpolarize things, which results in reduced glutamate. Glutamate typically acts as an inhibitor or excitatory depending on your bipolar cell. But light will hyperpolarize your photoreceptors in general. Okay, so let's look at kind of the makeup of our bipolar cells. Some have AMPA channels and some have mGluR6 channels. And depending on which channel that has, you'll either have increased glutamate release from the bipolar cell or decreased glutamate release of the bipolar cell. So let's look at AMPA channels. These will be stimulated by glutamate release and dark conditions. So if you have a photoreceptor that likes dark conditions, that means when you don't have light on it, it's going to send a signal, or it's going to hyperpolarize and stop sending glutamate to either a horizontal cell or it's going to stop sending glutamate to your bipolar cell. If you have mGluR6, it works through a second messenger which inhibits TRPMI or TRPM1 calcium channels. These calcium channels, if you are inhibiting them, you decrease glutamate release. And if you're decreasing glutamate release, which acts as an inhibitory, I don't know if you can even say that. Yes, actually, yeah, we're talking about bipolar cells, not photoreceptor cells. With bipolar cells, you either send more glutamate or you don't send glutamate. It really depends. So for mGluR6, you're going to decrease glutamate release, and with AMPA channels, you're going to increase glutamate release. How this works is AMPA channels will be off-center, and mGluR6 will be on-center. What I mean by that is light is going to affect the bipolar cell in such a way that if it is hitting it and it's an on-center bipolar cell, then it will release more. It will decrease glutamate release. If it's off-center, that means light, if it is not hitting it, then you'll increase glutamate release. So it's really dependent upon whether light is hitting it or not, and if we're releasing glutamate or not, right? So for AMPA channels on your bipolar cells, these are inhibited by light. they're excited by dark conditions, resulting in glutamate release. So for AMPA channels, if there's no light on them, then they're like, sweet, we're not inhibited, let's increase our glutamate release. For mGluR6, these are the opposite. If light hits them, then if light hits them, then it kind of switches the function of it. With AMPA channels, if light hits it, it turns it off. mGluR6, if light hits it, it turns it on so that it decreases your calcium channel activation, and thus you can't get rid of as much glutamate. So that's it's kind of confusing how that all works, but I hope through this next exercise I can explain a bit more. Horizontal cells, which will be connected to photoreceptor cells, will be depolarized by glutamate always. And when I say depolarized by them, that means that you will, if you depolarize, you release more GABA. So you'll receive glutamate from a photoreceptor cell, causing it to depolarize the horizontal cell, and that horizontal cell, because it's depolarizing, will now open calcium channels and release GABA. And GABA is an inhibitory signal for glutamate release on adjacent photoreceptor cells. And if you affect photoreceptor cells that are connected to bipolar cells, then depending on what bipolar cell you have, you either are more likely to send an action potential or less likely to send an action potential. So there's a lot of variables between if our bipolar cell sends a signal or it doesn't, and it's all dependent on if it is excited by glutamate or inhibited by glutamate. So there's a ton of variables which will switch things around and make y'all confused, but I hope I conveyed that somewhat clearly. So now let's look at this figure here. This is my representation of a receptive field. On the outsides, you have your surround field, and then on your inside, you have your center. Connected to each of these is your photoreceptor up top, and then below that you have a bipolar cell, and connecting your photoreceptors and your bipolar cells are two horizontal cells between them. So let's say that, we know that our horizontal cells always are stimulated by glutamate, which causes them to depolarize and send inhibitory GABA to this center photoreceptor, right? So if this center photoreceptor let's say it's on center, if light is hitting this on center, then it's gonna depolarize, it's gonna hyperpolarize, which doesn't allow as much glutamate to go into this synapse. And if glutamate is not going into this synapse with a bipolar cell that is stimulated by AMPA, then you're not going to send, and it's not going to depolarize, and you're not going to send an action potential. On the outsides, you have dark or off surround photoreceptors. So if light doesn't hit these surrounds, then you will depolarize these photoreceptors. If you depolarize those, you send more glutamate. The glutamate's going to hit your horizontal cell. The horizontal cell will increase its release of GABA, which will inhibit your adjacent photoreceptor in the middle. And if you're inhibiting the center photoreceptor, which wants to release glutamate, you have less glutamate going into this synapse. And if less glutamate goes into the synapse and you have a bipolar cell that is inhibited by glutamate, then with less glutamate, you're more likely to send an action potential. There's a lot of orientations for this scenario, so you really have to know whether your bipolar cell is inhibited by glutamate or if it is excited by glutamate. And that's dependent on if you have AMPA channels or mGlu or 6 channels. So in our case, because we're, at least for this bipolar cell, we're not sending as much glutamate, and therefore we're not inhibiting it, and therefore it will send an action potential down the bipolar cell, which therefore would mean that we are on center, we've excited it with light, decreasing our glutamate release, and it will send off a signal, a synapse to your ganglion cell. I know it's crazy and it's really confusing, but there's a lot of switches back and forth whether or not you're going to send a signal or not, and whether you don't signal can send a signal, but overall that's what receptive fields are, and it's important to know the role of GABA, how it inhibits glutamate release, as well as if glutamate is going to inhibit or excite a bipolar cell. And that's receptive fields for you. They help us detect edges and see sharp contrast.